Hi, and welcome to the last lesson in Unit 5, where we're still talking about titrations, but this time we're going to be talking about what happens when we titrate a weak acid or base with a strong acid or base. So we started our titrations learning about a more straightforward strong acid, strong base, or strong base, strong acid titration. And things are simpler with strong acids and strong bases because they 100% ionize and because their conjugates are weaker in water and cannot hydrolyze. Now things are going to get a little bit trickier because weak acids and bases, as we know, do not 100% ionize, and we know that their conjugates can hydrolyze with water. So let's start by just looking at a weak acid with a strong base. So here we have acetic acid being titrated with sodium hydroxide. One of the first things that you're going to notice as a difference between this curve and when we did a strong acid with a strong base is that our pH at the equivalence point is no longer 7. It is now greater than 7. And this is because, as you're going to see, when we get to this equivalence point, if we're doing a weak acid, then we have a conjugate base that can hydrolyze with water. So we actually have a basic pH at the equivalence point. We're also going to see that we have equilibriums present because we don't have 100% dissociation of our species. And so there's going to be some equilibrium reactions. And then our starting pH is also going to be a little higher than the pH with a strong acid due to that lack of 100% dissociation of the weak acid. So let's kind of look into what's going on at each part of our titration. So we're going to focus again on our 4 main regions of a titration curve. Before we reached the equivalence point, at the equivalence point, and then past the equivalence point. So here for our reaction between sodium hydroxide and acetic acid, we create sodium acetate and water. So for our net ionic, we lose the sodium, but notice we do not lose the acetate ion. So when this was a strong acid, when this was a strong acid and base, we lost both conjugates because both of them were spectators. But now this time our acetate ion is no longer a spectator. So that's a major difference here. Okay, so when we start, all we have in this flask is acetic acid. So in the beginning, we just have a weak acid. So the equilibrium that is occurring is acetic acid plus water creates the acetate ion and hydronium. So this is going to be a normal weak acid equilibrium. In region 2, so before we reach our equivalence point, some of our weak acid is going to have been converted into weak base, into its conjugate. So now we have this equilibrium set up. It's the same as the first one, but the difference now is we have both acetate and acetic acid in enough of a concentration to participate. So at this point, we've got a buffer at region 2. Then when we reach our equivalence point, we have converted every bit of the acetic acid into acetate. So now we have an acetate equilibrium reaction occurring. And then past that point, we are still going to have acetate, but we're going to have excess hydroxide, and that's going to take over. And it's going to be that excess hydroxide that controls the pH. So let's talk about how we're going to calculate the pH in each of these regions. So before the titration begins, as we mentioned before, we have just a weak acid. So this is going to be just a weak base problem. Weak base. This is going to be just a weak acid problem where we use an ice chart and Ka to solve for X, and then we take the negative log of the hydronium concentration. Then in region 2, we're going to solve it like an indirect buffer creation. Meaning, so we've got our acetic acid, we're going to neutralize some of it with our strong base sodium hydroxide to create acetate. And then when we figure out those new concentrations, we're going to use the Henderson-Hasselbalch equation to find the pH. At my equivalence point, I have converted everything into the acetate ion and then the spectator, but sodium's not going to do anything. So acetate is a weak base, and so we're going to treat this like a weak base problem. So you're going to have to calculate Kb, determine the concentration of weak base that we have at the equivalence point, and then do a normal weak base problem with an ice chart in Kb. And then after the equivalence point, we now have excess strong base, and it's that hydroxide ion that's going to take over control of the pH. So we just got to find out how much excess we have, take the negative log, and subtract from 14. Okay, so let's do an example of some pH calculations. So just like before with the strong acid, strong base, the first thing that we want to do is determine what our equivalence point volume is so that we know where we are, which region we're in on our curve. So I'm going to do MAVA equals MBVB. So the molarity of my acid is 0.1, and I have 100 milliliters of it. And my molarity of my base is 0.1. So my volume of my base, of course, then is going to be 100 milliliters. So at equivalence point, my volume is equal to 100 milliliters. Okay, so 0 milliliters added, I have just a weak acid. So I'm going to solve this like a normal weak acid problem. So I have acetic acid plus water My concentration is 0.1 molar. I'm going to start with initially 0 product minus x plus x plus x, 0.1 minus x, and x. So then I'm going to set that x squared over 0.1. I'm going to ignore my x because the k value is small. So then when I solve for x, I get 0.0013. And when I take the negative log, I get that the pH is equal to 2.87. So that's an acidic pH, which is what I expected. Because at region 1, I have only a weak acid. Now, in region 2, I expect to have a buffer because I am going to have both weak acid and its conjugate. So the first thing that I have to do is I have to determine how much of each of them I have. So I'm going to determine that I have 100 milliliters of 0.1 molar acid. So that's going to be, put this in liters, 0.1 liters. So I have 0.01 moles of acetic acid. And then for my base, I have 0.05 liters times 0.1 molar. So then that is 0.005 hydroxide. So I'm going to set up my reaction. So this is my neutralization reaction. Remember, I said that these are like indirect buffer problems because what I'm doing is I'm neutralizing part of my weak acid to turn it in to its conjugate base. So 0.01 moles and 0.005 moles. So minus 0.005 because as I expect, it's going to the strong base is going to be in a limiting amount because I'm before my equivalence point. So now I have 0.005 moles, 0 and 0.005 moles. So now my new volume is 100 plus 50, so 0.15 liters divided by 0.15 liters, and that is 0.03. So now I can plug this into Henderson-Hasselbalch. You also should recognize that these concentrations are equal. So pH is just going to equal pKa, which is 4.75. Now, in a little bit later, we're going to give this point an actual name, because remember how up here we determined that the the equivalence point volume was 100? Well, 50 is exactly half of 100. So in a later slide, I'm going to give this an actual name. This is the half equivalence point, and at the half equivalence point, pH equals pKa. So that only occurs at the half equivalence point, and I'll point that out again in another slide. So number 3 says 100 milliliters of NaOH. So we determined that 100 milliliters was the equivalence point volume. So I'm at the equivalence point, and all I have here is my weak base, because I have the conjugate of my weak acid. So the first thing I'm going to do is I'm going to determine how much acetate I have. So I have 100 milliliters, so 0.1 liter of 0.1 molar acid, and then I had 0.1 liter of 0.1 molar base. So I have 0.01 moles of each of them. So all of that's going to get used up, which is what I expected because I'm at my equivalence point. So I'm going to create exactly 0.01 moles of acetate, but now my new volume is 100 plus 100, which is 200 milliliters. So I'm going to divide this by 0.2, and that is 0.05. So now that is my concentration of acetate. So now I'm going to set up my equilibrium, because all of my acetic acid has been converted into acetate. So now what's going to happen is that acetate is going to hydrolyze with water to form acetic acid and hydroxide. And now it's just a normal weak base equilibrium problem. So minus x, and plus x. So now I have x squared over 0.05 equal to, oh, this is Ka, so I've got to find Kb. So that's 5.56 times 10 to the negative 10. So I'm going to solve for x, and x equals 5.27 times 10 to the negative 6. So I'm going to take the negative log of that, and that is equal to 5.3. 5.3. And then that means our that's our POH. So then our pH is 8.7, which is above 7, which is what we expected for the equivalence point of a weak acid with a strong base. Finally, in region 4, we have excess strong base. So we just have to figure out how much excess strong base we have. So same, we started with 100 milliliters of 0.1 molar acetic acid. Now we have 0.11 liter of the base. So 0.01 moles, and then we have 0.011 moles. So that leaves me with 0.001 moles of hydroxide. Now my new volume is 0.21 liters, so that is 0.005 molar. So now POH is equal to the negative log of 0.005. So the POH is equal to 2.3. So my pH is equal to 11.7. Expected it to be high because we have excess strong base. Okay, so now we're just going to flip everything. So now we're going to titrate a weak base with a strong acid. So this time our pH is going to be below 7 at our equivalence point, because the conjugate of my weak base is a weak acid that can hydrolyze with water. So we're going to have an acidic pH at the equivalence point. Just like in the last one, we are going to have equilibriums occurring because we don't have 100% ionization, and then we do have that conjugate that can hydrolyze with water. And then finally, our starting pH is going to be a little bit lower than it would be if we were starting with a strong base. So let's look at what's going on. The reaction that's occurring is ammonia plus hydrochloric acid is going to make ammonium and the chlorine ion. So we can take that chlorine ion out because it's a spectator, and so we're left with ammonia plus hydronium creates ammonium, or ammonia plus hydronium creates ammonium. So before titration, we only have our weak base ammonia, and so this is the equilibrium that's occurring. Before we get to our equivalence point, we have both the weak base and its conjugate, so we still have that same equilibrium, but like before, we now have a significant amount of both, so we've got a buffer on our hands. At the equivalence point, we just have the conjugate acid with its spectator ion, which isn't going to do anything. And so we have that weak acid equilibrium. And then past the equivalence point, we still do have that weak acid ammonium, but we now have excess hydronium, which is much, much stronger, and that's going to take over and control the pH. So before any titration occurs, like we said, we have just a weak base. So we're going to have this weak base equilibrium. So we're going to set up an ice chart. Before the equivalence point, we have that buffer. So just like before, we're going to solve it like an indirect buffer creation and use Henderson-Hasselbalch. At the equivalence point, we're going to expect an acidic pH because we're going to have just a weak acid. So we're going to set up a weak acid calculation with Ka. And then after the equivalence point, I just have to find the amount of unreacted hydronium and then take the negative log of that. All right, so let's do some example calculations for the weak base with the strong acid. So we're going to start at region 1, where all we have is the weak base ammonia. So we have ammonia plus water makes ammonium and hydroxide. So we have 0.6 0 and 0 minus x plus x plus x, 0.6 minus x, x and x. So we're going to set x squared over 0.6 equal to the KB. So x is equal to 0.033. So I take the negative log of that. Oops, 0.00. I'm sorry. And I get 2.48, which of course this is hydroxide, so this was POH. And so then the pH is equal to 11.5. A basic pH, what I expected. Okay, at region 2, I'm going to have both. So I have a buffer. So I have to figure out how much I have of each of them. Actually, let me take a step back for a second because I didn't do something that I told you guys to do, and I didn't find the equivalence point volume first. So let's take a step back. So my acid is 1 molar. I don't know how much it's going to take to get to my equivalence point. My base is 6 molar, and I have 90 milliliters of it. So I'm going to do 90 times 0.6 divided by 1, 54. So the volume at my equivalence point is 54 milliliters. My point in being, I know that 25 milliliters now is at region 2. Okay, so moving on. I have 0.6 molar times 0.09 liters gives me 0.054 moles of ammonia. And then I have 1 molar times 0.025 liters, 0.025 moles of H+. So I'm going to do my reaction. I expect the acid to be in a limiting amount, which it is. And it's going to create the conjugate. And now my amount of ammonia that I have left is 0.029. And then I have 0.025 ammonium. And my new volume is 25 plus 90, so 115 milliliters. 0.115 liters. Oops, not milliliters. It's 115 milliliters, 0.115 liters. And so my concentrations are 0.025, or excuse me, 0.25 and 217. So now I'm going to plug this in to Henderson-Hasselbalch. So pH is equal to pKa, but I've got Kb here, so I've got to find Ka. So 5.56 times 10 to the negative 10. And remember, it's always base over acid. Ammonia is my base, so 0.25 over my acid, which is 0.217. So negative log 5.56 times 10 to the negative 10 plus the log of 0.25 over 0.217. I get 9.32. So basic pH, which is what I expected, but it has decreased from my original because I did neutralize some of my base. So now 54 milliliters, we determined that 54 milliliters was my equivalence point volume. So I am at region 3 when I've added 54 milliliters of HCl. So the first thing I'm going to do is determine how much ammonium this created. So H plus NH3 created my ammonium, and I have 1 molar and I have 0.054 liters. For ammonia, I have 0.6 molar and 0.09 liters. So that gives me 0.054 moles and 0.054 moles, which, duh, what I expect, because at equivalence point, moles of acid equal moles of base. So you can really kind of take a shortcut on this if you would like, and once you know the moles of one, and then divide it by the new volume. So the new volume is 90 plus 54, so 0.144 liters. So this concentration is 0.375 molar. So now I just have a weak base problem. So 0.375, 0, 0, minus x, plus x, plus x, x squared. Oops. I'm sorry. I got carried away. We have ammonium, not ammonia. Okay, that's better. So x squared over 0.375, we have to set that equal to Ka, which I found on the last slide. So then I get that x equals 1, 1.44 times 10 to the negative 5. And we take the negative log of that, and we get 4.84. Which is an acidic pH, which is what we expected. And then finally, when we get to region 4, we have excess strong acid. So I just have to figure out how much excess strong acid I have. So I have 0.06 times 1 molar, and then of course still 0.6 molar times 0.09 liters. So I have 0.006 moles. Here I have 0.054 moles. Oh, excuse me. 0.06, that makes more sense. So then minus 0.054 minus 0.054, and I'm left with 0.006 moles of excess acid. So now my new volume is 60 plus 90, so 0.15 liters. That gives me 0.04 molar. So I just take the negative log of that. pH is equal to 1.4. So I have a strong acid, so I expected a really low pH. Okay, I alluded to earlier that I was going to have a later slide that was going to point out specifically the half equivalence point, and it's also called the midpoint. And so at the midpoint, exactly half of what we started with has been neutralized or converted into its conjugate. And so if exactly half of it has been converted into its conjugate, then we end up with a conjugate acid-base pair in equal concentrations, and so pH is equal to the pKa. So let's do an example. If I titrated 90 milliliters of 0.6 molar of ammonia with 1 molar HCl, so it's the previous question we had done. Okay, so
we determined that 54 milliliters was the volume at the equivalence point. So half of that is 27 milliliters is the volume at the half equivalence point. So what that would mean is that at 27 milliliters, pH has to equal pKa. So pH equals the negative log of Ka, which is 5.56 times 10 to the negative 10. And we get that the pH is equal to 9.25. Why is this important? Well, for one, it's a shortcut. If you're asked to determine the pH for a weak acid or a weak base titration, and you notice that you're at the half equivalence point, you literally just have to find the pKa. That's it. Another reason that this is useful is sometimes you'll be given a titration curve and you'll be asked, what is the pKa of this weak acid? And the way you figure that out is simply by looking at whatever the pH is at the half equivalence point. Okay, so let's kind of put this together by comparing a strong acid, strong base to a weak acid, strong base curve, and then a strong base, strong acid with a weak base, strong acid curve. Because there could be questions where you're simply given a curve and you're asked to determine, was this a strong acid, strong base titration, or a weak base, strong acid titration, or a weak acid, strong base titration? So let's kind of look at what's going on here. So for the strong acid, strong base, we notice we start at a lower pH because we have a strong acid, and then we have a very stark shoot up, and we have a pH of 7 at the equivalence point. Now for our weak acid, strong base, we start at a higher pH because it's a weak acid, and then we get this nice buffering region. We also are going to have that special point of the half equivalence point where pH equals pKa. And then we have our pH is greater than 7 at the equivalence point because of that conjugate base being able to hydrolyze with water. Now we kind of can make the same comparisons over here. For the strong base, strong acid, we start at a higher pH because it's a strong base. We have this stark shift, and then we've got our pH equal to 7 at the equivalence point. But now if we look at our weak base, strong acid, we start at a lower pH when compared to the strong one. We have our buffering region. We also have this nice half equivalence point, and then we get our pH less than 7 at the equivalence point due to that conjugate acid hydrolyzing with water. Okay, a few more things for this and we will wrap it up. So I've mentioned before that we do use acid-base indicators in titrations, and acid-base indicators are just weak organic acids or bases that change color with changing pH. And so we can think of them as this equilibrium below. This would be IN is the indicator. And then there's the version with the proton and then the version without the proton. So it's kind of like an acid with a conjugate base. Okay? And so if we add an acid, that's going to shift it to the left. And so we're going to get whatever color this version is. But if we add hydroxide, that uses up this hydronium, which shifts us right, which means we're going to get whatever color this side is. So for example, for phenolphthalein, as we become more acidic, it's colorless, and as it becomes more basic, it is pink. So all different indicators have different color change intervals. So like what pH range the color actually changes. So for titration, we want to choose an indicator where the color change interval includes the equivalence point. Because if we pass our equivalence point and the color still hasn't changed, we're not getting any use of our indicator. So when we are titrating with a base, we always pick an indicator with a pKa around 1 less than the pH at equivalence point. For the base, we want 1 less. And then if we're titrating with an acid, we want an indicator with a pKb 1 greater than the pH at the equivalence point. So in this example, we see the phenolphthalein changes around 8.7, so that's going to be good for when we have a pH that's greater than 7 at the equivalence point. Litmus range, so if the pH is 7 at the equivalence point, and then methyl orange changes at an acidic pH, so that's the one we would want to use if we're titrating a weak base with a strong acid. Okay, last but not least, we have polyprotic acid titrations. And so remember, a polyprotic acid means it has more than one hydrogen that it can donate. So example, H2SO4. Okay? So a couple things to know with a polyprotic acid titration. You're going to actually see an equivalence point for every acidic hydrogen. So for example, let's say that this was a titration curve for sulfuric acid, H2SO4. This first equivalence point is for the first hydrogen, and the second equivalence point is for the second hydrogen. So that's because, if you remember when we learned about polyprotic acids, they only give off one hydrogen at a time. So this right here is the first equilibrium, and then the second is the HSO4 minus, giving up its hydrogen. So this first midpoint is equal to the pKa of this first hydrogen, and the second midpoint is equal to the pKa of the second hydrogen. And if you remember, those should change because the Ka's go down as we lose subsequent hydrogen, so the pKa's are going to go up. Now, you are not going to have to do any pH calculations for a polyprotic acid curve. All you're going to need to be able to do is, if I showed you this curve, you need to be able to recognize that it's a polyprotic acid with two hydrogens, and recognize that each midpoint corresponds to the pKa of each subsequent hydrogen, and that's it. Okay, so that wraps up our Unit 5 notes. We are halfway through with notes for AP Chemistry, y'all. That's huge. All right, so I will see you again soon.